This is Unit 7, Electrons, Part 3 notes. At the end of this unit, you should be able to understand the electromagnetic spectrum and the mathematical relationships between energy, frequency, and the wavelength of light. You should also be able to calculate the wavelength, frequency, and the energy of light. So electromagnetic radiation is just the form of energy that displays characteristics of a wave as it moves through space. The electromagnetic spectrum is the full range of electromagnetic radiation, and we should be able to describe the electromagnetic spectrum based on wavelength, which is represented by this lambda symbol. It's like an upside down Y. Frequency is the variable F, and energy is the variable E. If we look at the EMS spectrum, we have gamma rays all the way to the extreme left, and then we have all the way through long radio waves on the right. You should have gotten a handout with this EMS spectrum on there, so you don't have to really draw this. If you want to color code the visible light spectrum at the bottom, you can, which will be very helpful. But we need to know which type of wavelength has the lowest frequency or the lowest to the highest energy. If you look at the waves, the one to the furthest right is your radio waves. These have the longest wavelength. All the way over to gamma rays, these have the shortest wavelength. Okay, then frequency would be the opposite, to where the highest frequency is all the way to the left, and then the shortest or the lowest frequency is to the right. Okay, in terms of energy, which we'll discuss the relationships in the future slides, gamma rays have the highest energy, while radio waves have the lowest energy. And we will relate all variables through mathematical formulas on the next slide. Okay, so your wavelength is described by the lambda symbol, looks like an upside down Y, and it's just defined as the distance between two crests or peaks, and it's usually measured in meters. So if you look at the picture to the left, we have a wavelength, which is either the peak to the peak or even the crest to crest. And you can have different numbers of waves through a specific unit of time. If you look at the top wave and the bottom wave, that relates to what is known as frequency, which is the number of wave cycles to pass a given point per unit of time. This is measured in hertz, which is equivalent to 1 over second, which is also equivalent to second to the negative first power. And if the more wave cycles you have, the higher the frequency, and the shorter or the lower the number of waves, or the lower the number of wave cycles per unit of time, the lower the frequency. So these variables are inversely related, to where the more wave cycles you have, the shorter the wavelength, the higher the frequency, and then the longer the wavelength, the lower the frequency. Okay, so we can relate wavelength, frequency, and energy based on two formulas where we just previously talked about wavelength and frequency. They're inversely proportional, because if one goes up, that means the other one must go down. And they're related through the speed of light, which is your variable c. So through this formula, c is equal to your frequency times wavelength. It's right here. C stands for the speed of light, which is 3 times 10 to the 8th power meters per second. F is your frequency, which is your hertz unit. And then wavelength is your lambda symbol, usually notated in the unit meters. Then if you look at energy and frequency, we can relate them through Planck's constant, which is noted as 6.626 times 10 to the negative 34th joules times second. These are actually directly proportional. He used mathematical relationships in which he said the amount of energy of a single quantum or unit absorbed or emitted by a body is proportional to the frequency of radiation. That just means the higher the frequency, the higher the energy. If you look at the diagram to the left here, we have gamma all the way to the right, has a very short wavelength, high frequency, which would end up having a high amount of energy. The radio waves all the way to the left have the longest wavelength, so they have the lowest frequency and lowest energy. So we're going to be using these two formulas on the next page, where we can relate frequency and wavelength through the speed of light, and then we can use the energy in joules is equal to Planck's constant times frequency. Frequency can either be in the variable f or this italicized v. Okay, so your first problem is, what is the wavelength of yellow light in nanometers emitted by a sodium lamp if the frequency of radiation is 5.09 times 10 to the 14th hertz? Using the speed of light, c is equal to 3 times 10 to the 8th. So we're going to relate frequency and wavelength through the speed of light. In solving for the wavelength, we have to divide both sides by frequency. So your wavelength is going to be equal to the speed of light divided by frequency, which is 3.00 times 10 to the 8th meters per second, over your frequency, 5.09 times 10 to the 14th hertz, or 1 over second. That should be 14. So taking the top number divided by the bottom number, we end up getting, let me erase some of this if you want to write that down. We get 5.89 times 10 to the negative 7, but that's in meters, because if you take meters per second and try to divide by 1 over second, you can't ever divide fractions, so we have to flip. So then you'd have meters per second times second over 1, you end up with meters. The answer wants us to be nanometers, so we must convert using dimensional analysis, where meters come straight down to the bottom, nanometers goes at the top. In 1 meter, there's 10 to the 9th nanometers, so your final answer with the correct amount of sig figs should be 5.89 times 10 to the second power, and then your unit nanometers. The second problem, we're calculating the energy of a quantum of microwave radiation with a frequency of 3.20 times 10 to the 11th 1 over second, also known as hertz, using Planck's constant. So if E equals h times f, h is Planck's constant, which is 6.626 times 10 to the negative 34 times 3.20 times 10 to the 11th 1 over second. Multiplying those two numbers and rounding to the correct amount of sig figs, we end up getting 2.12 times 10 to the negative 22nd joules. So that's 2.12 times 10 to the negative 22 power in the unit joules, because you have joules second multiplying by 1 over second, and we end up with the unit joules for energy. Okay, so have you accomplished the objectives of this unit? If not, please either rewatch the video or ask me questions the next time we go over these problems in class. Make sure you get the electromagnetic spectrum handout so you don't have to draw all of the diagrams and pictures, and just be prepared to go over this on the next class period.